In this video, we are going to talk about the Reynolds transport theorem. And the Reynolds transport theorem is a method that allows us to use both system and control volume concepts to describe fluid motion. So let's start here with picture number 1. And we'll call the red our system and our blue our control volume. And the control volume is a fixed place, whereas the system is considered a certain amount of fluid. So here, at some time, both the system and the control volume take up the same space. However, at time plus a small bit of time, what you've noticed is the control volume stays the same. However, our system, which is that amount of fluid that we're looking at, moves. And so what we do is we use the Reynolds transport theorem to link the two of them. So we start with the fact over here that the change of some extensive property, so B is an extensive property of the system with respect to time, equals rho times some intensive property that's associated with the extensive property times the change in volume. And we do the same thing right here. However, it's our change with respect to time in our control volume. And what we're left with is this equation that says that the time rate of change of some extensive property here of the system is equal to the rate of change of the property as it flows through the control volume. So if you notice, that's with respect to time plus the flow in and out of our control surfaces. And our control surfaces are anything that is a surface of our control volume. So let's take a look at a typical problem. And we have this system here, this control volume, and we have a velocity 1 here, which is 2 meters per second, and it has a diameter of 0.07 meters. We have a second velocity here with a diameter of 0.03 meters. We have a third diameter, but what we want to do is find out what the velocity there is. So if we look at our governing equation, the first thing that we see is that in this particular problem, since it's a conservation of mass problem, our big B is going to equal mass, which makes the intensive property that's associated with mass 1. So if you look at the change in mass of the system with respect to time, that has to equal 0. Then when you look at the first term of the right-hand side, what you find is that this mass does not change in the control volume with respect to time, so that equals 0. So what we're left with is that 0 equals, and let's go back to here, the integral over all of our control systems of rho, remember little b is 1, v, which is a velocity, dot n, so that's the dot product of the velocity and the unit normal coming from the control surface, times our differential area. So how many control surfaces do we have here? We have 1, 2, and 3. So we're going to have to set up 3 separate integrals looking at all 3 of those control surfaces. 0 equals the integral over control surface 1 rho v dot n dA plus this integral over control surface 2 rho v dot n dA, and finally over control surface 3 rho v dot n dA. Now there are a number of things that can make this equation simpler. First of all, we're going to assume that rho is constant, that it's incompressible, so we can take it out of the integral. And if we do that, you notice that we can then cross out rho. The second thing that we know is that our velocities are constant or uniform, therefore they are not a function of area, and we can take the entire term out of the integral. So what we're left with is 0 equals v1 dot n times a1 plus v2 dot n a2 plus v3 dot n a3. So what is this v dot n? Again, it's the dot product of our velocity times the unit normal coming out of the control surface. So if we have flow in, then v dot n is negative. If we have flow out, v dot n is positive. So let's go back to our picture again. And if you notice that flow in is our V3, so V3 dot n is positive, and our flow out is both V1 and V2. Let's write this as 0 equals V1 is going out plus V1A1. V2 is leaving the control volume, so that's plus V2A2. And finally, V3 is entering the control volume, so that's minus V3A3. So what we're looking for is that V3. So we can rewrite this as V3 equals V1A1 plus V2A2, all divided by A3. Knowing that the area, it's the cross-sectional area, and the cross-sectional area of a pipe is pi over 4 d squared. When we put in our values, what we find is V3 equals 1.07 meters per second.